Okay, this is Mr. Zanaletto. I'm doing some more proofs here, doing some geometric proofs, and do the odds for this extra practice. The first thing they say is that AC is congruent to BD. So I mark that on my diagram just so that I get some idea of what's happening. Then I have AB plus BC equals AC. Well, first of all, this was given. AC equals BD was given. Those lengths are equal. Then they have the two lengths that make up this segment are equal to the total length of the segment. So that's segment addition postulate. And they do the same thing with the second one. BC plus CD equals all of BD. That's a segment addition postulate. And then we go ahead and we substitute in. We're substituting in AC is here, AC is here. We're going to go ahead and substitute this for AC. We're going to substitute that for BD. That's how we get this. BD is going in here, and AC is going in here, just like it was up there. So we're putting what AC stands for, we're putting what BD stands for. It's substitution. So that's substitution property. That's how we're justifying that step. And then we go AB equals CD. We're subtracting away BC from both sides. How did this step change from this step? Well, both sides had a BC to start with. Now they both don't. So we use subtraction property of equality to subtract them away from one another. So subtraction property of equality. That's how that proof shapes up. And again, this is somewhat of a geometric proof, although it's not a very complicated one. It's pretty simple. The next one we're going to do is number 7. Number 7, again, we're given A, B, C, D, all are on this line. And they also tell us a congruency. They tell us that AC is congruent to BD. That's congruent to that. And that was given. Now if they give you the segments are congruent and then they say the segments are equal, that's the definition of congruency. Definition of congruency. From there, we have AC equals AB plus BC. That's again part and part equals the whole part. That's segment addition postulate. And we do the same thing for BD equaling its two smaller parts. So that's segment addition postulate. Now, once we have that, I'm going to go ahead again. AC is here. Well, this is what AC equals. And BD equals this. Well, I can plug that in for BD. So I'm plugging things in. That's by substitution. I have AB plus BC equal that BD piece, which is CD plus BC. That's substitution. And once I have that, now the next piece that I want to do is I want to subtract BC from both sides. I get AB equals CD by subtraction property of equality. And once I have that, then by definition of congruency, I'm done. We go back to segments being congruent by definition of congruency. And that's number 7. And the last one I was going to do in this video is number 9. Number 9, we look at this and we see CD bisects. This is doing the bisecting. It's bisecting AB, which makes this congruent to this. Makes this congruent to this because this bisected it. This was given. And AM equals MB. How? That's by definition of bisect. And if the two segments are congruent, their two lengths are equal by definition of congruency. Been using that quite a bit today. Now, how do we get AB equals AM plus MB? I don't see anything up here that's really making that true. So then I look over here and I see AB is that bigger piece, AM's part of it, and MB's part of it. That's segment addition postulate. Because we're adding the two smaller segments, and we get the larger one, segment addition postulate. Now, how did it change one step to the other? Well, we substituted in AM for the MB. We substituted that in, so that's substitution. We knew those two things were equal, so we go ahead and swap them out for each other. That's substituting. Then, this next step has been somewhat debated how we should name this, but I would say it's combining like terms, so that's what we'll call it, combining like terms. The only thing is we don't have that on our reason list, which I'll talk about in just a second. Combined terms, which is really just like opposite of distribution property. If you really wanted to use a reason for it based off our reason list, I would say distribution. And once we have that, we go ahead and multiply both sides by 1/2, and we get exactly what we wanted. So we multiply both sides by the same thing, multiplication property of equality. And we're done. So those are those 3 proofs. They have a little bit more of a geometry feel to them, although they're not real expansive. But we're talking about a lot more lengths than angles and stuff. We do have like with the angles, but this gives you an idea of how to do some geometric proofs. Thank you.